Namaskar, my dear friends. Let us talk about a C2000 series real-time microcontroller system design. So the device that we have taken is TMS320F280039C series, okay? And the package will be 100 LQFP package, okay? 100 LQFP package. So as you can see, if you want to have, like some other devices, you can utilize any one of these four devices. So these two are non-automotive parts and this is automotive part. This part and this part is both are same because it is just like a reel, that's all. So F280039 CPZ RQ1, okay. Otherwise non-automotive part it will be F280039 CSPZ. All right. So what we'll do is we'll try to understand what are the different blocks of this particular circuit and how to design each one of them. All right. So let us start with system circuit design based on real-time microcontroller that we have been already seeing for past few like sessions. And as I told you already, the target device that we are going to take up is F280039 CSPZ. Okay. So these two are non-automotive part with C and without C. Without C is very low cost one. Okay. And this is automotive part. The blocks that we will see for this particular microcontroller system is this particular thing. So what we will be seeing? We will be seeing power supply and safety and protection. We'll see power supply management. Then we will see, like JTAG programming and reset. And also we will have various peripherals. So various peripherals, if you want, you can, like list them one by one. Like we have connected one ADC for potentiometer measurements. We have 12 PWM so that like you can drive two BLDC motors. Okay. Then we will be having ADC monitoring for different voltage rails and different signals. Then we have CAN transceiver, LIN transceiver interfaces. We also have different sensors like humidity sensor, temperature sensors. We have audio buzzer as well as we will be taking up two DAC outputs from this particular microcontroller. We have one more EEPROM I2C interface so that we can save the data through I2C communication. We have external interface so that you can like send your PWM signal or fault signal or like some other power supplies to other router card. Then we have various IOs to do some other jobs like having deep switches. We have push buttons for some like user inputs. We have LEDs blinking. Then we have USB to UART bridge as well so that you can directly connect it to your USB and through UART you can communicate through your microcontroller board. So this is like one of the best thing that we have always. Then we have SPI communication as well. So SPI interface is there, two SPI is connected, and we have SCI UART interfaces for other purpose. So these are the things that we will be seeing in our circuit system design. So let us open one by one and we see. So as you can see, the very first thing that we have to do is we have to design this particular microcontroller symbol. Okay, so as you can see, all the GPIOs are arranged in left side. All the GPIOs are arranged in left side, then few of them are also put in right side. Similar to that, we have power supply pins, like top side, and power supply ground pins are bottom side. Then we have analog pins right side here, and we have JTAG programming pins here and reset pin. All right. So this is how the pin, like arrangement has been done. Since this is 100 pin device, so I have just made a single IC to incorporate all the pins in a single package. All right. Coming back to the power supply. So power supply we need VDD, VDDIO, Vreference and analog voltage and VREN-Z. Okay. So that I will tell you what it is and all. Okay. So what happens is this VDDIO pin will be requiring 3.3 volt. So this 3.3 volt is coming from VDD after a ferrite bead filtering. Okay. And then four pins were there. So four decoupling capacitors will be needed. This is how it is made. Similar to that, we have VDD pin that will be requiring 1.2 volt. That is actually taken from internal regulator. So this will be taking power from VDD IO internally, and it will just need external decoupling capacitor. All right. So what we do is we just connect like this. Then we have VDA pin. So VDA decoupling capacitor is here, and we have a reference pin. So reference also is given from here. So reference is actually generated 3 volt, and VDAC reference is also taken from that reference only. All right. Good. So this was all about decoupling capacitor. Coming back to the programming part. So programming connector is this. We have 10 pin like a standard programmer of 1.27 pitch. Then we have all the signals like TMS, TCK, TDO, TDI, and reset signal. So this is how JTAG programming is interfaced with the microcontroller that we have. So these are the JTAG programming signals that we have in the microcontroller. All right. Coming back to the external reset circuitry. So external reset circuitry, what we have done is we have one XRS signal that is coming from the microcontroller from this point. Okay. And if you press this particular push button switch, then what will happen? It will pull this to low, and this is how the microcontroller will reset. We have also added one external crystal oscillator to generate high frequency clock. So that is 12 megahertz like external clock is there, and it will be getting connected to external like XTL X1 and XTL X2. So this is how it is going to connect here. So this was all about the essential circuits that was required. Now let us talk about the peripherals that has been connected in this particular microcontroller. So as you can see, we have utilized all the PWMs. Total 8 pairs were there. PWM 1A, 1B up to 8A, 8B. So up to 6A, 6B only will be used because there is no need to use 7A, 7B, 8A, 8B. These are just redundant. Okay. So this is how PWM signal has been generated. Now coming back to the clock out. So clock out pin is taken out. So if you want, you can utilize this clock out to drive some other, like a processor or something like that, wherever there is a need. Then we have LIN transceiver output. So LIN TX, LIN RX, and then we have SPI B. So SPI A is here. SPI A is here and SPI B is here. So there are two SPIs, both of them have been used in this particular system. We have SCIA communication as well, and this is also capable of having UART communication. So I have like renamed it SCIA underscore UART TX and UART RX. Similar to that, we have I2C communication, and then we have CAN communication as well. So CAN TX, CAN RX. And similar to that, we have other part like we have USB user dip switches, user push buttons, and user LEDs. So each one of these circuits we will try to see one by one. Okay. More than this, what we have is we have analog connections. So analog pin, just quickly we will talk about. So we have this DAC A1 output, DAC B1 output. Then we have temperature sensor for an like ADC measurement. We have temperature sensor and humidity sensor in a single package. One more. We have potentiometer analog pin, and then we have voltage level measurements for VCC and VDD. So VCC is 5 volt and VDD is 3.3 volt. Then we have current sense for like a current sense resistor of U, V and W phases in the IPM. Somewhere you will utilize, or motor driver circuit you will utilize. So you have sense U, sense V, sense W. Okay. Similar to that, second pair is U2, V2, W2. We have over temperature sensing also from the IPM, like intelligent power modules and all utilizes VOT signal. And we have fault signal, fault indication that is coming to the GPIOs that is there. So this is how a complete like a pin mapping and pin configuration has been done. Let us move to the next funch. So as I was talking to you about like humidity sensor and temperature sensor, so this is the IC that is taken from Renesas HS4101, and that is capable of having temperature sensor as well as humidity sensor. So after this output, they have been like buffered and filtered, and then send to my ADC pin of my microcontroller. Okay. Similar to that, this also humidity sensor has been buffered and filtered and sent to my ADC MCU. So this was all about temperature sensor and humidity sensor. Now let us talk about a UART to USB bridge. So this UART to USB bridge, what is going to happen is we have TXD signal and RXD signal of this particular UART to USB bridge from silicon devices, silicon lab, okay, and this is going to give us USB positive and USB negative signal, that is D plus and D minus, that is getting connected to my micro USB connector, that is USB N and USB P. And this particular lines is also protected through ESD diode of this particular like ESD array, that is taken from Worth Electronics. This is a part number 824011. Okay. So this was all about USB to UART bridge, and very nicely, it has been powered by 3.3 volt, a single voltage level. If you want, you can power this up by V bus as well. That is not a problem. So if you want to utilize that features or something like that, or you want to have a different kinds of utilization for this particular device, you can reach out to us and we will be able to give you a option to how to power up this particular device through V bus. Okay. Let's move to the next one. We have some discrete devices as we have been already talking to you about. So like we have one audio buzzer. This is a magnetic transducer. So this particular magnetic transducer will require 2.73 kilohertz PWM signal of 50% duty cycle. Okay. So this PWM signal, one of the PWM8A has been used as a buzzer signal, and this buzzer signal will be, uh, voltage divided here and then send it to this particular transistor. And this is how this particular audio buzzer will have a beep sound for alarm purpose or something like that. This is very, very useful because you need to have some alarm for some faulty condition or some other purposes. Then we have potentiometer connected. So this potentiometer can have a variation by varying this particular knob, and this particular knob variation will generate a different voltage level at this particular place, and after filtering we are sending it to my analog ADCs. Okay. Coming back to the voltage measurement, so we have two voltage levels on the board, like one is 5 volt, that is VCC, and one more is 3.3 volt, that is VDD. So these two has been a voltage divided, like voltage division is there, and this particular voltage division, let us say Vx1 is there, which is going to get buffered and then filtered and then send it to my microcontroller ADC pin. Similar operation is done for this 3.3 volt also. So this 3.3 volt has been buffered, filtered and then sent to my ADC pin. We have onboard EEPROM. So this particular EEPROM IC has been taken from microchip technology, that is there, like for 4 kilobits of uh, memory, and this is going to have a I2C interface. So very simple I2C interface design for, like a EEPROM interface, I2CA SCL and I2CA SDL line, that is going to get converted here. And as I was telling you, one more, a very simple temperature sensor IC has been used to have a temperature measurement, and this is going to give you 10 millivolt, like increment for each degree centigrade rise in temperature of your board or environment, whatever it is. Okay. So after filtering, we are sending it to my ADC pin of the microcontroller. Okay. Let's move to the next one. So we have some of the IOs that has been used for user push button 0, user push button 1. So what is going to happen is whenever this particular push button will be pressed, so once you press it or push it, what will happen? This will get grounded. So basically this particular microcontroller pin user PB0 will receive a 0. So whenever push button is pressed, my microcontroller will see a low signal, and when it is not pressed, you will see this is connected directly through 3.3 volt power supply, so that will see a high. So not pressed means high, not pressed means high, and pressed means low. So similar to that, user PB1 is also happening. We have deep switches. So deep switches, what is happening is we have deep switch 0, deep switch 1. So these two pins is capable of like generating 00, 01, 10, 11 state. So these four states can be generated by these two pins. So what is going to happen is, this is right side, it is closed. So as you push it right side like this, then what will happen? 3.3 volt will appear on that particular pin. Similar to that, we push it left side, then it will become open circuit. So it is grounded, it means you will see 0. So based on these two pins, you can generate total four like options of states. Then we have LEDs. So user LED 0, user LED 1, 2, they all are driving a MOSFET to switch on and switch off the LEDs. So as my microcontroller signal goes high, what will happen? This particular MOSFET will switch on, and this is how my LED start glowing. Okay. If you want, you can remove this 0 ohm resistor and directly sort it. Okay. So that you can reduce one resistance uses. So that is more than enough. And when you want to like switch off the LED, what will happen? You have to just press it, like send it low. So low signal will like switch off this particular MOSFET, and this is how your LED will start switching off. Like it will glow, it will go off. Okay. So this is the same operation is there for user LED 1, user LED 2. So if you have any like concern regarding the current variation of the like LEDs, so you can vary the resistances. Okay. Or if you want to if you want to drive this LED by 5 volt, what you can do is, this particular 3.3 volt can be made to 5 volt also, and this is how this particular LED will be driven by 5 volt signal or VCC signal. Okay. All right, so this was all about the like user IOs and like LEDs, push buttons and everything that we have just now seen. Let's go back to the next one. We have CAN transceiver. So in this CAN transceiver, what happens is, basically we are having controller side CAN TX, CAN RX signal that is going to get voltage translated. So basically this is my 3.3 volt signal level that is coming, and that is getting converted to 5 volt level. So we have CAN TXD, CAN RXD. This CAN TXD, CAN RXD is going to get converted to my like CAN high and CAN low signal by this particular CAN transceiver. So what I have done is, we have a power supply pin, we have CAN TXD pin, CAN RXD pin, we have ground, and we have CAN high, CAN low. So this CAN high, CAN low is going to get proper termination of 60.4 ohm with like split configuration, split capacitance. And then we have filter capacitor of each of the line, and then we have ESD diode protection for each of the CAN high and CAN low signals. And similar to that, this particular connector will be giving you an interface to the outside world by having a proper power supply pin as well as CAN high and CAN low signal, so that you can drive the external board. We have grounded this STB so that this particular CAN transceiver will always be in normal operation mode. If you want to like control this, you can directly connect it to one MCU GPIO. Okay. So when GPIO goes low, it will be working. When GPIO goes high, it will not be working. So this is how you can save the power. Now let us see a lean transceiver. So this lean transceiver which we have taken is having fault protection with inhibit and wake up operation as well. Okay, so these are the capabilities that is there for this lean transceiver that we are going to talk about right now. So we have T-Lin 2021A that is there from Texas Instruments. So what is going to happen is, we have lean RX signal and lean TX signal that is going to get converted to my lean bus signal, and this lean bus is filtered and ESD protected and then send it to my lean bus. Okay. So this is made in commander mode. So this commander mode operation, what happens is, you have to pull it up through this particular diode and resistor. It is pulled up. Okay. And the power supply that you want, you can give it from here. So one connector is provided here to give a 12 volt power supply, up to like to 20 volt, 24 volt also you can give, not a problem. And this particular pin is going to go to my supply pin that is there, 12 volt with ESD protection and like diode protection circuits with capacitances. We have not used inhibit operation, inhibit feature. So inhibit is like grounded directly with 100 kilo ohm resistor. And we have enable pin as well in this particular lean transceiver. So this enable pin is permanently enabled. If you want, you can drive it through a microcontroller GPIO also to enable disable this particular lean transceiver. Okay. So if you want to disable this, you have to pull it low. You want to enable this, you have to pull it high. Coming back to the wake up pin, so wake up pin is also permanently made it like enable like V supply directly. So if you want to disable this, or let's say you want to make this in sleep mode, what you have to do is we have a lean wake up pin that is coming from my microcontroller, which will be driving this particular MOSFET. So once this goes high, what will happen? This will go low, and this is how it will be in sleep mode. Okay, so this lean wake up pin, one of the pin of the microcontroller, can be given directly. Let's go back to the next one. We have power supply pins. So we have power supply operation, like a 6 volt to 18 volt supply you can give through this connector or one adapter jack that is given. And this is going to get fuse protected and then going to V in A. So this V in A is going to get converted to my 5 volt 2 ampere output that is there using this particular switching regulator. Okay, that is there from analog devices, one of the most important switching regulator that we have been using. Then for my microcontroller signal or microcontroller power supply, we need 3.3 volts. So this VCC is going to get converted to VCC to 3.3 volt, zero point 0.5 ampere output that is there from a linear regulator of ROM semiconductor. Okay. And this particular, like a 3.3 voltage being monitored through an LED. So this LED will be glowing when 3.3 volt is available. Similar to that, 5 volt is also being monitored through this LED. So whenever there is no fault or something, this VCC is there, then what will happen? This particular LED will be glowing. Okay. If this particular IC shows any faulty condition or any problem, then this reset will go low, and this is how what will happen? This reset will go low, so this particular MOSFET will not be working, and this is how this LED will go off, and you will understand that okay, my 5 volt is not appearing in the board. For the V reference generation, what we have done is we have used one IC to generate 3 volt of like V reference to be utilized for ADC as well as DAC operation. Okay, so this 5 volt is going to get converted to 3 volt for that purpose. So hope you have now a very good understanding about how this particular microcontroller circuit is working, and what are the different peripherals that we had used to do that job. One thing you can add is this part, let us say one of the GPIO, you can name it and put it lean wake up. Okay, WAKE up. So lean wake up control that can be done by one of the GPIO pin, because we have lean TX, lean RX, and wake up signal was also required. So this was all about this particular microcontroller system that we had talked about. So all the block diagram and different peripherals connection of this particular microcontroller that we have seen. If you do have any questions or any queries regarding the peripheral connection, or how to start with a design, how to select components, you can put down your questions in the comment box, and we shall be able to answer you out as soon as possible. Thank you.